Some kind of shenanigans in here. All right. I will begin. I will attempt to begin with a word of prayer. So I find something here. So let me begin. Heavenly Father, we thank you for this day. I thank you for these students. Just ask that you just bless our work today and just help us to glorify you in what we do, Lord. In your name I pray, Lord Jesus. Amen. There's no CFARs here, right? It's not time yet. We're still safe, right? You're a CFAR? All right, so let me see if I can find some problems. You guys asked me about the homework.
Mr. Cook?
Yeah.
Are we accounting for present for last lecture?
I'm passing the attendance sheet around so you can check both places there. So as I've told you guys before, I don't really use Top Hat for the score in terms of like counting absences. I use the sheet that you're checking or not checking at the moment. So nevertheless, I am obligated to run the Top Hat every day, so I do. Let's see here. So last time we looked at rational expressions, and I showed you a bunch of different algebra steps to do to simplify rational expressions. I think the next thing on our list of things to do is to solve equations and inequalities involving rational expressions. So that's what we'll be doing today. And I think we'll start with equations. And so let's see, I think those are maybe section 1.6 kind of problems. So let me look in there, see if I can find some. Yeah, here we go. So let's work some of these. And so I'm hoping I hit, one of you showed me some problems before class that I've assigned you. Well, I don't have a, so if I miss a problem of a particular type after I'm done with a few of these, you know, push me in the other direction, all right? So, there we go. Wookiees aside. How would you solve? Now this one's really simple. We'll start out real easy. Yeah, 1 over 4x minus 2 over x equals to 3. How would we solve this equation here? This is number 15 in section 1.6. Yeah. Well, you could do that, but I think we could be lazier. How about this? Could we factor x out of this? How about this? I could do this, right? 1 over x, 1/4 minus 2, right? If that makes sense, does that make sense to you or no? Or I just say we could factor out 1 over x because I've got 1 over x times 1/4 and then 1 over x times minus 2. So if I do that, that gives me 1 over x times, how many quarters is 2? 8, right? So 1 minus 8 is minus 7/4. And so this gives me 1 over x is equal to 3 times minus 4 over 7, also known as minus 12 over 7. And then, so if you get that, then if you want to solve for x, you can just reciprocate both sides. So if you flip both sides, This?
No. The next step below. That.
I never write, if you're asking me if that's a mixed fraction, that's very offensive to me that you would have asked me such a thing. You know I hate those. How dare you? No, it's multiplication. I'm multiplying 3 times minus 4/7. Yeah.
So you're just multiplying the opposite side by the reciprocal? Is that correct?
Yeah. Multiply by the multiply by the reciprocal of this to cancel it out. Or if you like, divide both sides by this number, gives you this. Once I get to here, I can flip, and I get x is equal to minus 7 over 12. I like to put the minus upstairs just as a point of. Now, doubtless, some of you will not like the way I just did this, right? Here's another way to work this problem. If the way I'm doing it leaves you uneasy, here's another way to do this problem. 1 over 4x minus 2 over x is equal to 3, right? So you don't like the way I did it. Fine. Another way to do this would be to multiply the equation by x. Multiply both sides by x, what would happen? So the x is here, and the x is here, cancel. And what we get is we get 1 over 4 minus 2 equals to 3x. And what, you like this better? Fine, yeah. And then what? This is minus 7/4 equals to 3x. So x is equal to 1/3 of minus 7 over 4, also known as minus 7 over 12. So as I've told you before, if you're a postmodernist, I've got bad news for you. Math is not a good place for you. There's just one answer. It doesn't depend on your life story. Sorry, it's not a conversation. There's just truth. Sorry about that. You can choose your opinions, but you don't get to choose the facts. What can I tell you? Let's see here. So let's work another. Let's see here. Something a little bit more interesting. Number 17. Example 2. Here we're up against 2x plus 5 divided by 2. Now you were asking me a second ago to make a common denominator, right? And that's generally a good idea. It's just I didn't need to for that last problem, so I resisted you. But you could have done that. That would have been another way. You're not wrong. So here, what should we do? I mean, there's two schools of thought. The one school of thought would be make a common denominator, go from there. I'm inclined to try to destroy the fractions. What's that? Take out the 2 in the denominator. And what, you mean cancel these? That we cannot do. You don't mean that, though. You just mean write it as a half. I mean, you could do this.
Did you just do the cross multiply?
This is the same expression written in a different way. I mean, you could do that. I don't know if that helps us, but yeah.
Could you cross multiply?
Cross multiply in what sense? You mean like put these two together?
Like 2x plus 5 times x.
So you want to do 2x plus 5 times x minus 2 minus 2 times 3x, all divided by 2 times x minus 2 equal to x. That's a good thing to do. Sure, we could do that. So yeah, we could make a common denominator like that, and then once you do that, what would be the next logical move? By the way, what's our game plan here for solving these? Our game plan ultimately is either to get a fraction equal to 0 or to convert it into a polynomial equation, which we know how to solve. If we get a fraction equal to 0, the only way a fraction can be 0 is if the numerator is 0. So that's simple. I'll do my next example like that, okay? This one here, I'm inclined to multiply by the denominator to convert it to a polynomial problem. See, because if I multiply by 2 times x minus 2, I've got 2x plus 5 times x minus 2 minus 6x, right, is equal to 2 times x minus 2 times x. Which might not look like progress to you, but it is, because now we're dealing with a quadratic equation, which we can solve. Yeah?
Can you explain how you got that to 2 versus x minus 2 and x equals 20?
How I got the, from here to here? I multiply both sides by 2 times x minus 2, so it cancels on this side and it doesn't on the other. So, generically speaking, the pattern is this. If you've got a over b is equal to c over d, then we can rewrite this as a times d is equal to b times c. Like, that's generically speaking the pattern. So it just so happens in this problem that the d is just 1. So it's kind of, in this situation, we're kind of more like this. A over b is equal to c, right? So we're trading it for a is equal to b times c. That's the pattern that we went through here. And now let's multiply it out, right? What do we got? We've got 2x squared plus 5x minus 4x minus 10 minus 6x is equal to, if I multiply this out, I've got myself a 2x squared minus 4x, I believe. Oh, hey, I said this was quadratic, but I spoke too soon. Is it quadratic? It's only, yeah, only in appearance, right? Because this and this, they'd be canceling. And, oh, what else cancels? Check this out. Whoop, whoop. Whoop, whoop. And what you got?
-1x.
Yeah, negative x minus 10 equals to 0, also known as x equals to minus 10. Yay. Solved. All right. Are there other ways to solve this problem? Probably. Are there other easier ways to solve this problem? Probably. Let's go on, though.
I have a question.
Yep, go for it.
Can you always cross multiply how we did? Like could have we done that with 1 as well? Like how we...
Yeah, I mean,
Yeah.
that's what I did over here, is I just multiplied by x to make the fractions go away.
Mhm.
That's equivalent, essentially, to cross-multiplying there.
Okay. So like we could have done 4x times 2.
Yeah, a third way to do example 1 would be this. This is actually 1 minus 4 over 4x equals to 3, which would give us minus 3 is equal to 12x. I think I did something wrong. What's 2 times 4? Is it 4? It's 8. There we go. So minus 7. So then x is equal to? Minus 7 over 12. Yay. All right, so there's yet another way to work problem 1, which apparently is easier. Yep.
Why didn't you make that 8x? Like, wouldn't that...
My common denominator was 4x. I already have an x here. I just need to multiply that by 4 over 4, logically. So I'm just taking 4 over 4 here to get to this step. Yeah. Yes?
Tuesday, you were talking about if we were doing a division problem and you said we couldn't cancel out a certain part of it. Could you do it? I can't remember which part.
Okay, so what I was saying there was you got to be careful. If you cancel, if you divide things out, you might be changing the domain. So anytime we do division like that and we lose track of something, that might be part of the interesting part of the story, right? Like, for example, if you're dealing with an equation where x equals to 0 is a solution, and then you divide the whole equation by x, you might lose track of the fact that x equal to 0 was a solution. Here, for example, like this. This happens all the time with students, like x squared equals to x. People get this problem on an algebra exam, and what do? They're like, oh, I know what to do. I'll just divide the equation by x, right? Divide by x, what do you get? You get yeah, x equals to 1. Oh, answer, right? That's true. But that's half of the answer, because x squared equals to x also has the solution 0. And see, that's the cost of dividing by x, is like we lose track of where that's 0. And that might be part of the answer. That's what I was saying last time in a nutshell. Is anytime you do division, cancellation of things like that. Hey, let me work another problem here. It is... let's see here, example 4. What if we're up against 3 over x minus 2 plus 1 over x plus 2 is equal to 12 over x squared minus 4. So what would you guys suggest I try there?
Give back to the x squared minus 4, then do x squared to x minus 2.
I should do. I didn't quite follow you. What'd you say? What'd you say, Bethan?
So
Aw, man.
12 over x squared minus 2, x minus 2, x plus 2.
Oh, sure, I could do that. But, well, I'm going to resist the urge to do that, though, because that won't help us directly. I don't... Well, will it help us? Maybe it will. Maybe, yeah. I'll follow your lead. Why not? Let's see here. Your point is, like, this is actually that, right?
Yeah.
So maybe writing that helps you see something. What should we do to this equation to make it pretty?
And then
What should I, let me ask the question in a more leading way. What should I multiply this equation by to make it nice? X? Be greedier. That's good, that's a start. I like x plus 2, but let's do more. Let's multiply it by x plus 2 times x minus 2. If I do that,
you cancel 3 plus 1 is equal to 12.
right. So I'll write it out. So it multiplies by that, right? But it also hits this term here, right? And on the other side, I'll write it out, but you already know what's going to happen. So when we multiply the equation, we have to multiply every term by whatever we're multiplying, right? But it works different on each term here, right? So like the rightmost term, like you guys told me, this just leaves us with 12. But on the other hand, over here, this one and that one cancel, right? And here, this one and that one cancel. And so what do we have? We've got x plus 2. Don't forget your 3 times 3, right? Plus x minus 2 times 1. That's less exciting. All of that's equal to 12. And now we have reached a problem that you all should be like, yay, I can solve that, right? I can solve that all day long. No problem. Yes? I hope. I mean, let's finish it. So let's see here. I've got a 3x plus 6 plus x minus 2 equals to 12. Let's keep all our x's on the left-hand side, put all numbers on the right-hand side. So I got 4x is equal to 12 minus 6 plus 2, also known as 4x equals to 8. What's that? What was the question? I didn't quite follow yet. But.
I'm looking at my own work versus what I did first.
Let's see here. Go for it.
Okay, so I got where you got 3x plus 6 plus x minus 2 is equal to 12, right?
Mm-hmm.
And then what I did is then I combined all the like terms on the outside and set it equal to 12. So basically I got 4x minus 4 is equal to 12. No, because can I? Because
He's saying that what he was tracking what you said. He said that +4 should have been a -4.
No, it should be.
Or I'm wrong.
no, but like, why did you put it 4x is equal to that, and then it's not even like set like that in the equation?
I was putting all those things.
So yeah, what I see these two guys I put together to give me the 4, right? This 12 is exactly that 12. And so I'm subtracting 6 to the other side, and I'm subtracting 2 to the other side, which means I'm adding 2 to both sides.
Because I'm questioning what I did versus what you did.
Oh yeah, I don't know.
Because when I brought it down, like, I got what you got, then I got,
But did you get 2?
no.
Ah.
No, I got 4.
Huh.
Because what I did is I didn't put like the 4x on one side, I did combine the like tangent and
She combined the
4x.
6 and
Mine, I.
Did you have
So
6?
you combine the 3 and the x, the 3x plus x is 4x minus 4 is equal to 12. And then,
Did you have a -6 in your work?
okay, wait. Let me do something fast.
Here, no.
I just feel
Here, let me just look at your board for a second. Oh, did you erase the thing?
Yeah, but I think I know what it is.
Well, it's right up to here.
Yeah, because then
Yep.
let me just try to.
So whatever happened, it was the last step that got you.
Oh, wait, you're right. I said I did wrong.
Yay. So, you know, it's a very frustrating thing when you can't see like your mistake and it's like right in front of you. I know myself today, I have this thing I'm calculating and like I know that it should be positive, the thing I'm calculating, but it comes out to something negative and it doesn't matter how much I look at it, I cannot see the error. Uh-huh. Is this good? Do you need to see more of these, or did you need to see more of these, or is this good? This is good. Let me do one more of these. I'm going to do number 33 from section 1.6, and then we'll go on. What example am I on? 5. Ah. You rolled out? I excommunicated the marker, huh? All right, very good. Somebody just walking down the hall minding their business, all of a sudden this like marker's like, then they're gonna fall and sue me. No! All right. I wasn't here, I didn't throw that marker. Right? Okay. Just remember that. So this one suggests a particular technique, right? Like this one just yells at you, cross multiply me, right? So you just, oh, thanks. Okay. I'm not sure what's going on over there, but I'll allow it. All right. Thank you. All right. We still have other things to do today, you know. So I multiply. This is cross multiplication, right? And then how do you solve this? Well, work it out, right? So this is 6x minus 15 is x squared minus 2x. Aha, so this is x squared minus 8x plus 15 equals to 0. Yeah.
And you get x minus that.
I moved everything to the right-hand side.
Yeah.
Yeah.
X minus 3x minus 5.
Mm-hmm.
Yeah, and then x is equal to 3x equals 5.
Right, yeah, so minus 2 minus 6 is minus 8, and when I move the minus 15 to the other side, it becomes plus 15. And then I put the 0 on the other side. So if you like to be more truthful to the last line, it's this, right? Fine. That's what I did. I moved everything here over there. Can you solve this? How do you do that? Oh, man, you guys, dang it. I was hoping we were going to complete the square, but you just factored it. That's good. Yeah, we don't need completing the square here unless you don't see this, right? But since we saw it, we don't. So what our solutions are, x equals to 3 and x equals to 5. Whenever you have this kind of problem, if there's division involved, it's just a good idea to check and make sure that these make sense for the problem. They do. If you plug in 3 and you plug in 5 into the equation, the formula makes sense, right? Yep.
That's the first time on the example 4. When you plug in 2, it doesn't work.
Ah, very good. So x equals 2 doesn't work. Ah, thank you. Thank you, thank you, thank you. I got distracted. Yes, there's more to say here.
Or me.
And this is extraneous because the original equation is undefined at the one place where the algebra works out. So what is the answer? So no solution. No solution.
No solution.
I believe. A little bit bothered by this.
Did that problem come from the book?
Yeah. Oh, yeah, which one it is? It might have been an even one, though. What is it? You got a question? Yeah, it was 22. That'll help. Yep.
How can you, like, is there a way to test for no solution or extraneous solution?
Yeah, at the end of the problem, you have to like go back to the start and see if it still makes sense or not. Yeah.
How do you know which problems to cross multiply and which problems to like multiply by something?
You can do both for many problems. It's not like mutually exclusive. Like these are just tools. So, you know.
So you could cross multiply that problem and get the same answer.
Yes, but you'd have to. Okay, so since you asked, another way to do the last example, example 4 here, I'll do it here, would be to make a common denominator on the left-hand side. So to do that, I would do 3 times x plus 2 plus x minus 2 divided by x plus 2 times x minus 2. So I'm making a common denominator of the left-hand side. That would be equal to 12 over x squared minus 4. Now, this upstairs becomes 4x minus 8 over x squared minus 4 equals to 12 over x squared minus 4. That implies that 4x minus 8 is equal to 12, which gives us 4x is equal to, what? 20. Funky. X is equal to 5. What? Oh, this is weirding me out. Yeah. That's interesting.
Where did the -8 come from? Because you got.
Oh, yeah, I was hoping this was more exciting. Like, this would have been very exciting, but it's not. Yeah, thank you. 3 times 2 is 6. 6 minus 2 is 4.
I was like, what?
There we go. Yeah, okay. Well, that's less exciting. So apparently 4x is equal to 16. Well, unless I've made a mistake, which seems entirely likely.
So it was not complete.
So you got, did you get 4?
Well,
No.
that was a coincidence of the last
So
one.
all this unchanged by the, oh, okay.
Huh. 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 Interesting.
Yeah, that's what I did. The last one.
Huh. 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 Very interesting. Does 4 work? Hey guys, is 4 a solution? No? Did you check? How do we check if I'm right or not about the 4? Assuming I haven't made some stupid mistake. Let's check it, right? So we've got 3. Please stop talking. I can't think when you guys are talking. 4 minus 2 plus 1.
The answer is no solution. I photomathed it and photomathed
You photomathed it. Well, forgive me if I don't trust photomath here. Let's see here, 4 squared minus 4. Look here, I'm plugging 4 into the original equation. If it works, it works. So it may or may not. I think it should. I think it's going to. So let's see here. That's 3 over what? 3 over 2 plus what? 1 over 6, which is also known as that's 1? Oh, this is 1?
Yeah.
Oh. Oh, but this is not 1.
Yeah, you're right.
I think this is 20 over 6, yeah? Which of course is not equal to 1.
Wait, shouldn't it be 10 over 6?
12. Well, okay, so if you wanted to do 6, it's fine. Yes. That'd be better. 10 over 6. Which is indeed not equal to 1. Huh. I don't know what's going on here, guys. This is really weird.
Do you want me to show you the steps photomathed?
No. I don't care about I don't care about photomath steps. I care about what I'm curious about is what's going on here. Huh. So, all right, guys, please stop talking. Thank you. So, it's very bizarre to me that 4 doesn't work here because I don't feel like we've made any step here which is incorrect for 4. Like the common denominator, 3 over, I did this 3 times x plus 2, and then 1 times x minus 2. Like this seems right to me. And we fixed that, right? That was 4x plus the 6 minus the 2 is, oh, right there. Look at that. Come on, guys. That's a plus. You guys corrected my correction, but you didn't make a correct correction. So it's all your fault. Let's see here. Just kidding. So that's what?
No, but that still gets us back to 2.
That gives us 4x equals to 8, which gives us x equals 2. There we go. That's much better. Which, of course, is extraneous because that does not work, right? No, we do not. No. That's not how this works. Like, we have.
Wait, so
No.
is it x equals to 2 or is it no?
So, and this does not work. Not a solution. Why is it not a solution? Because we go back to the start and, I can do better than photo math. Like if you guys will just let me take the test for you, then I will improve the S rate in here vastly, yes. What's that?
No, hypothetically say like, I don't know, I was going to say about a test question.
So these things can happen on the test. I mean, there are problems that you solve, and the only solution that the algebra suggests is a solution which is extraneous. I mean, this happens. Okay. Sorry, the 4 was really bothering me. I'm glad we found that. Example 6. Yep.
A question. How do you know if it's like that kind of a solution when you like if you completely like do the problem and you get like a totally not answer that's like, for example, like put a if x in that solution is equal to 4 or if x is equal to 2, like how would you be able to?
How would you?
Like.
Well, I mean, if you incorrectly got the minus here, right, on the test, suppose you do like I did, and you put the minus there, and you get through it, and you find x equals to 4, right? And then you plug it back into the original equation, and it doesn't work, and then you say, therefore, it's not a solution, then I'd probably give you most of the credit, because you're mostly, like, your solution method is mostly right.
Mm-hmm.
So,
so you would count it right if you just put like.
I think you'd still lose some points because you made a mistake, right? But
would we get credit for putting like no solution on it?
Well, yes, but it's not just the answer I grade, right?
Yeah.
I mean, if you want me to just grade answer, we can do multiple choice instead. You don't want that. No good comes of that.
I like that.
No. That is not an offer. Okay, so here's one. Let's see here. So 2x plus 3 times x plus 10 divided by x squared plus 4x plus 5 times x minus 1 equals to 0. So what are the solutions? Yeah, this, if we complete the square on that,
X plus 4, x plus 1?
so that's prime. All right. So what? What are the solutions to this? So one of the things I was telling you guys is if you have a fraction, the only way it can be 0, right, is if the numerator is 0. So once you find if you have the equation in this form, you can just say, okay, so all I have to do is I have to solve 2x plus 3 basically times x plus 10 equals to 0, all right? Keeping track where you came from, we have to check the original equation at the end of it, make sure we don't have an extraneous solution. And so this gives us what? Either, yeah, x is minus 3 halves. x equals minus 10, right? And if you go back and you try these solutions, in the original problem, they're fine. The reason for that, what's the trouble in the original problem? The denominator, right? Where is the denominator going to be 0? Only one number. The denominator is 0 only at 1. How do I know that? Yeah, because the x minus 1, that becomes 0 if we put x equal to 1, right? And this is prime, which means it's never 0. So the only thing that could be extraneous for this problem would be x equals to 1, which is not a solution that we found. So these are solutions. Yeah.
So why did you just get to eliminate the whole bottom, including x minus 1?
Because the only way for a fraction to be 0 is for the numerator to be 0. If I have a over b is equal to 0, the only way that can be true is if a is equal to 0.
You mean
What?
would b have to be 0, or it would have to be?
No, a has to be 0. If I have a fraction where b is 0, it's just undefined.
Oh.
That's a different problem. If I'm just looking for it to be 0, then it suffices for the numerator to be 0. If the denominator is also 0, then it's extraneous. All right. Let us go on. We need to talk about inequalities. How do you solve rational inequalities? What do you guys think we're going to do?
Complete the square.
Complete the square. I guess that's part of it. Here, we'll start out with example 6. But instead of putting equals, we'll put, well, you guys pick it. Do you want less than or greater than? Greater than it is then. And I'll put greater than or equal to 0, just to be interesting. So how did we solve polynomial inequalities? How were you supposed to have solved polynomial inequalities on test 1? How will you solve polynomial inequalities on the final exam? Critical numbers, and we draw a number line, right? Some of you are not drawing the number line, and so I don't know, I have no idea what you're doing. So the critical numbers here. Now critical numbers for us before were where the polynomial was 0, right? Now we've got a denominator. So the critical numbers are what? They're either where the numerator is 0 or where the denominator is 0. Either one of those are places where the sign of the expression could change from plus to minus. So critical numbers for this are minus 3/2, minus 10, and 1. The x squared plus 4x plus 5, as we just discussed in the previous example, is prime. It's never 0. It doesn't give us a critical number. So we draw a number line, like so. And so let me give this thing a label. Let me call this thing f of x, okay? So here's the number line for f of x. I need to put my critical numbers in order. Minus 10 comes first. Minus 3.5, well, that's next. 3.5, listen to me. Minus 3/2, also known as minus 1.5, right? And then 1's over here. Where is 0 in all this? It's in this, right in here, right? 0's like here. What would f of 0 be? We'd do what? 3 times 10 divided by 5 times minus 1, right? Because if x is equal to 0, you just look and just keep the numbers. That's how the function evaluates at that point, yeah? And so the larger point here is that this is what? This is less than 0. So because of that, I can put minuses up in here. The sign flip theorem I told you guys about before still works. All the factors here are linear, so we can just flip the signs as we go across. So like this goes pluses over here, it's pluses over here, and minuses over there. So there's my number line. Once I draw my number line, then I can solve the inequality. Yep?
Why is the f of 0 not equal to 0? It like doesn't have the line under,
Why is it not equal to 0?
like up top.
0 greater than or equal to, then that's less than
Oh, well, yes. So what that means is that 0 is not in the solution set. We're looking for all x that happens. This apparently is 1x where it doesn't.
And so how did you know that was the plus? Like where to put the plus?
Oh, well, because all of the factors are linear, we don't flip signs. So like if I did another example, to answer your question, it's best to answer your question with another example. If I had x minus 1, x minus 2 over x minus 3, x minus 4, and let's suppose we put a square on this one and this one. If I solve that was less than 0, less than or equal to 0, my number line would have a 1, a 2, a 3, a 4. And in this case, if you plug in a really large positive number, it's all pluses, 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 pluses. So I could start out pluses here. 4, I wouldn't flip because it's a square. At 3, 3 is this linear, so I flip. At 2, 2 is linear, I flip. It's just it's power 1. And then in 1, it's a square, so again, I don't flip. So this is the sign flip theorem. If I know one case, I can propagate the signs to the other places. Now, the other way to do this, which is more laborious, is to plug in a number in each case. I can literally plug in a value in each case. So like I plugged in 0 here because it just was easy to me. If you think about plugging in a large positive number, what happens if you plug in like 1,000 into this? Basically, you've got 2,000 times 1,000 divided by 1,000,000 times 1,000. That's a positive number. So that's why we had pluses over here. If you plug in like a minus 1,000, you get like a minus 1,000, a minus 1,000, a million, because the minus 1,000 squared is like a million, and a minus 1,000. So the net, the sum total of it is you got minus, minus, plus, minus. 3 minuses is a minus. That's why you got minus over here. You can plug a number in to figure out the plus and the minus, but I personally find it much easier to figure out one case carefully and then use the sign flip theorem to propagate the signs from there. Yeah.
For the final answer for 7.
Oh, I'm not done yet. Yeah.
Oh, okay.
Yeah. I was responding to her question because to see to understand why I did there, you have to see what I would have done if it was different, which is example 8. So here I had the squares. So when there's a square, we don't have the sign flip. But what's the answer here, though? Let's go back to 7. What's the answer? So once you have the number line, we can read the answer from the number line. Okay? So the solution set, what is it? We're looking for pluses, right? Looking for greater than or equal to 0. So I've got pluses from minus 10 all the way over to minus 3/2, and also from 1 to infinity. I have not drawn the parentheses yet, and I want to talk to you about what should we do there. Yeah, that's a question. Should they be brackets or should they be parentheses? Why or why not? Brackets. So this is a bracket, this is a bracket, union, this is a bracket. I disagree with one of these choices. Which one? And why is it different? Why is this one not like the others? Why does this one not belong? Y'all know your Sesame Street, right? Oh. Actually, no one's watched Sesame Street. What am I talking about? This one here, no. I shouldn't do that. Why shouldn't I do that? Why does this have to be excluded? What's the difference there? That's coming from the denominator. That if we put x equal to 1, we have division by 0. That does not solve this inequality. It makes the expression on the left-hand side undefined. In contrast, minus 10 and minus 3/2, when we plug those in, that makes the numerator 0, which makes the fraction 0, which means greater than or equal to is true. All right? That's the difference. So we do keep the minus 10 and the 3/2. We need to exclude the 1. And that's it. That's the solution. Yeah.
So we're excluding the one. So like if it was not 1, that was like just because it's in the denominator, it's excluded, or just
Yeah,
because it
it's-
would make it 0?
It's because it's in the denominator that's excluded. Can't divide by 0, right? How about this one? What would the solution set be over here? This time I'm looking for less than or equal to 0, right? So I'm looking for the minuses. Oh, just here, right? So apparently 2 to 3. Now, do I exclude or include? Bracket both was half wrong.
Oh, bracket 2.
Bracket 2? I got to vote for bracketing 2. How many people say yes? I would agree with that, because that makes the numerator 0, which is desired, right? And how about 3? Well, 3 we need parentheses, because that would be division by 0. We need to exclude the 3. There you go. Now, is there more though? Let's be careful. Less than or equal. Can I make it equal to 0? What is equal to 0 here? This one's a little bit tricky. I could either do 1 or 2 for making it 0, right? Have I included 1 in my solution yet? I haven't. So annoyingly, this one I have to take the union with the singleton just containing 1. Weird, right? So, anyway, yeah. Mm-hmm.
And we're including the 1 because it's like, because we know it's a critical number.
Because it makes the expression 0, and we're solving less than or equal to 0. So anything that makes it equal to 0, we have to include in our solution set.
Even though it's not like touching the negative part of
Right, right. Now, if we instead were solving this, x minus 1, so same expression, right? Same expression, but suppose we just put less than 0, what would the answer be then? What's the solution set then? Right. It's just 2, 3, and neither of them are included. Because we're not looking for 0. If we're solving less than 0, equals to 0 is not allowed. So, here's example 9. So actually, once you have an expression, once you've found the number line for a given expression, you can solve pretty much a whole bunch of inequalities that are related to it, right? You can do greater than 0, you can do less than 0, less than or equal to, greater than or equal to. All 4 of those problems you could solve from the same number. Once you have the number line, you can solve all problems related to this. But you notice something? In order to do this, we have to have the expression is what? It has to be a single fraction, right? It has to be a single fraction equal to 0. And if we don't have that, then we need to make it happen. All right? So like, see if I can look at some of those. Yeah, let's look at some problems where we're not given. So the problems I've started you with are kind of nice in that they're already set up. They're already ready to write down the number line so we can solve it. So, if you didn't get the number line idea for the last test, I hope you can get it for this test because it's important. And it does come up again on the final when we circle back to doing the polynomial stuff. Also, when we're graphing polynomials and graphing rational functions here before long, it will still be important there because it's what guides our thinking, the whole number line idea. So if this sign flip theorem I said is slipping past you, if you're not quite getting it, you need to stop, pick an example, and focus on it until you see it. See what we're doing, okay? Here's one. Example 10. What if I'm up against where'd it go? Minus 5 over 3x plus 2 greater than or equal to 5 over x. This one's sufficiently annoying, I think. I lost it. Where'd it go? Well, I think we can solve it whether or not The bad thing is if I've inadvertently copied the book problem half wrong, then we'll have an ugly answer. Yeah.
You subtract 5 over x from both sides and set it greater than or equal to 0.
Okay, but what if we, I mean, I like your idea, but let's, the opposite thing. Let's put this one to the other side. But yeah, move everything one side. How about this? So 0 is greater than or equal to 5 over 3x plus 2 plus 5 over x. Photo math. You guys are funny. Is this really the problem in the book? Is there a 5 both places? I feel like I've copied this down wrong. No, that's it. This is number 76 in section 1.7. So, by golly, when you have something like this, divide by 5. Divide by 5. This is something you can do to an inequality, right? You can divide by a non-zero number. So 0 is greater than or equal to 1 over 3x plus 2. Otherwise, we're going to be multiplying stuff by 5, which is just kind of dumb. Let's do that. All right, now life is a little bit better. No 5s. What's our next move? What's that? Yes, common denominator is the way to go here. So make a common denominator. How do we do that? Yeah, x times x plus 3x plus 2 over 3x plus 2 times x, right? So I make a common denominator. I multiply x to the one, I multiply 3x plus 2 to the other, and my denominator is the product of the denominators. I think that cleans up a little bit. This is really what? 4x plus 2 over x times 3x plus 2. All right, great. Now, I guess we could factor a 2 out, couldn't we? Maybe that's worth doing. This is 2 times 2x plus 1, right? And downstairs we've got x times 3x plus 2. All right, so we're solving. So to reiterate, our problem is apparently just 2 times 2x plus 1 divided by x times 3x plus 2 greater than or equal to 0. That's what we're up against. Can you solve that? I mean, we can solve this, right? What we have to do.
We take 1/2 and 2/3 out as critical numbers.
Aha, yes. What are the critical numbers? I like that. Critical numbers are negative 1/2. How about 0, right? And would you guys tell me minus 2/3? I think I believe that. If I plug minus 2/3 into 3x plus 2, that gives me 3 times minus 2 over 3, which is minus 2. Minus 2 plus 2 is 0. Yeah, I think you guys are right. These, if we plug those in, they will make either the factor upstairs or these factors downstairs be 0. So these are the 3 critical numbers. Now we do what? Make the number line. Yep, and then we got to test a point. All right, so my number, which one comes first? Yeah, negative 2/3 is the most negative number there. Then minus 1/2. Then 0. So where do you guys, so what does the sign flip theorem say here? What has to happen at every critical number? Since we have linear factors, each one, wherever we start, it's going to go plus, minus, minus, plus. It's going to flip each time. Each time we hit a critical number, it's flipping because there's no square, right? They're each just linear. So where do you guys want to start? Well, that's the one thing we can't do. So we can't plug in. The one thing we can't do is plug in these. These are not helpful. Anything else other than these 3 numbers? What's that?
Oh, 1.
Plug in 1.